we're talking about Newton's first law, okay? Inertia, the tendency of an object to continue doing whatever it was already doing, okay? Traveling at a constant velocity or remaining stationary, okay? Because it will do either one of those things as long as there is no what? No net force, okay? There can be forces, there can even be many forces. They just all add up to 0, okay? At the end of the day, we were talking about how your car's safety systems are designed around, well, restraining you, let's say, okay? Making sure that your inertia is not something that is going to harm you, okay? That is the whole purpose of a seatbelt, okay? Is to keep you in the car. If you don't wear it, inertia will allow you to leave the car. Okay? And other than that 1 in a million case where the car rolls over and the person is ejected and they somehow live, okay? The other 999,000 times that happens, it doesn't go that way. Okay? Because sometimes people talk about like, oh, in a rollover, you're way better to be ejected from the car. Well, we talked about projectile motion at the end of the last unit, right? If your car is doing this, okay, and rolling like this, where are you going to be ejected? Or when are you going to be ejected? Because the door's on the ground here, right? You're not going to be ejected there. Okay? If you're going to be ejected, it's going to be probably along this part of the arc. Where is that going to throw you? Exactly. Who's going to move faster? You flying through the air or your car rolling along the ground? You flying through the air, which means you get to lay there on the ground and wait for the car to roll over you. Okay? It is always better to be in the car. Okay? It's designed to keep you safe. Now, that does not, of course, account for operator error. Okay? You get yourself into a rollover, okay? That was probably operator error, or somebody else's operator error. Okay? But obviously, it's designed to keep you safe, okay, in all situations. Now, what I want to show you here is some crash tests, okay? And you can kind of compare how well does each one of these cars keep your inertia from hurting you, okay? And you can kind of watch the motion of the dummies, okay? I'm not being insulting, that's what they're called, okay? The things they put inside the car, okay? You can see their movements, okay, as they go along, which are pretty representative of what the human body would do. And you can see how well are they controlling the inertia? How well is the car, you know, remaining self-contained and not changing its shape, okay? Or in some places changing its shape a lot to protect you, okay? Okay, so your seatbelt actually uses Newton's first law in order to activate. Right? So do your airbags. Okay? When airbags first came out, they were a contact switch. Okay? So in the bumper were little switches that had a little gap in them. Okay? And if something hit the front bumper, it would push it and would complete the circuit and would detonate the airbag. The problem was you could walk past the front of a car, kick the bumper, and set off the airbag. Okay? There's actually like a video, and I think it's fake, but it's funny. Okay? Of this, like, there's this old lady in a walker. She's like crossing the street in front of this like convertible Mercedes, and the guy is honking at her, and she's just a little old lady. She's just trying to get across the street, and she finally just loses it and takes her purse and smacks the front bumper, and dude's airbag goes off in his face. Okay? Old airbags, you could do that. That's how they were built. If you got in a crash, okay, it would destroy the bumper, the switch, the circuit would be completed and blow the airbag. Obviously, that's not ideal. Okay, I mean, you know, there's people out there that are really bad parkers, right? And then they park by sound, right, instead of by vision. And oh, I can't go any further that way, and boom, off the airbag goes. So they weren't as reliable. So now they actually use the same technology that your phone uses to tell you which direction you've oriented it. Okay, there's like a little metal cage with a ball inside. Okay, and so when it experiences any acceleration, the ball will make contact with the wires and complete the circuit, and that will detonate the airbag. So it's basically the same thing as this, okay, but with a kind of a metal cage, right? So if you stop suddenly, the ball goes forward, and I mean, if there's enough tension in there that it doesn't go off unless basically you've come to a stop dead from 50 kilometers an hour. Okay? That'll send it forward, that'll set it off. That's why airbags don't always go off. Okay, like I have yet to be in a crash, okay, where my airbags have gone off. Okay, I've had a few accidents. One of them was my fault. The other ones were not. Okay, where my airbags, I got in a crash, but the airbags didn't go off. We weren't going fast enough to set them off, or the acceleration that was produced wasn't enough to set them off. Okay, that was the one I described yesterday where I won. Okay, I won the collision because I was driving the bigger vehicle. Okay, my vehicle didn't experience enough acceleration to detonate the airbags. Lady in the Ford Focus, not so much. Okay, her car was a complete write-off because I had driven the front end of our Expedition about halfway through the engine compartment. Okay, and then I got out and went, buff that, that'll buff out. Okay, like I had to replace a headlight assembly, but other than that, it wasn't too much. Okay, that's where mass matters. I simply had more inertia. Okay, and because she got pushed back really rapidly, okay, that sensor detonated the airbags. Okay, making some sense? All right. Now, let's talk about something we're going to use a lot here in this unit, and that is what we call free body diagrams. Okay, so the free body diagram is going to be kind of like your givens when you're doing a Newton question. Okay? The free body diagram shows all the forces that are acting on an object and what direction they act in. Okay, so right now, let's say that the object in question is this microscope. Okay, if I set it on that desk, okay, I could draw a free body diagram of that microscope that would look like this. Here's the awesome thing about free body diagrams. Everything's a box. Okay, you never have to draw an actual picture of the object. Everything is a box. Okay, all we write inside the box is the mass. I don't even know what the mass this is. Okay, this is about 6 kilograms. Okay, so I've got a 6 kilogram mass sitting on a level surface. What forces are acting on that microscope right now?
Gravity.
Gravity, okay. Okay, so I put gravity in there, and I show which direction it's acting. Down. Is gravity the only force acting on it? If gravity was the only force acting on that microscope, what would it be doing? Falling, okay. What's keeping it from falling?
Desk.
The desk, okay. So the desk is exerting an equal and opposite force upwards. We call that the normal force, Fn. Okay. Near as I can tell, those are the only two forces acting up there. There's no like wind or anything in here. Nobody's pushing it one way or another. Those are the only two forces. Okay? I could even calculate those forces if I wanted to. All right? Calculating the force of gravity is actually pretty straightforward. You have the formula on your formula sheet. The force of gravity is mass times the acceleration due to gravity. Okay, so that would be 6.0 kilograms times 9.81 meters per second squared, okay, which should be 58.86 kilogram meters per second squared. Okay, so the force of gravity is 58.86 kilogram meters per second squared. That's a mouthful. Can I say that shorter? What are the units for force? Newtons. That's a Newton. A kilogram meter per second squared is a newton. Mass times acceleration. That's how we calculate force, mass times acceleration. Okay, so that is a newton. Since the microscope's not moving, how big is the normal force? The same. The net force is 0 because it's not moving. If the net force is going to be 0 and I have 58.86 newtons acting downwards, I best have 58.86 newtons acting upwards. Okay? Because those forces are equal and opposite, the net force is 0, and we see that this thing is obeying Newton's first law. It is remaining still because there's nothing to accelerate it. Okay? Everybody with me there? All right, so free body diagrams are fairly easy to draw. Okay? I mean, we're going to get to the point where we'll have some and they'll have 3, 4, 5 different forces on them. Okay, some of them will be angled. They'll kind of get a little bit crazy. Okay, but this is how you start out. Okay, you always start out a Newton question by identifying how big and in what direction your forces are acting. Okay, now, how did I know those added up to 0 besides they were the same number? Okay, this one was acting up, this one was acting. Did I essentially do this? I just put them tail to head, didn't I? Okay. Force is a vector quantity. We're still going to be doing tail to head vector stuff in this unit. Okay. And it'll still work. Okay. We add all vector quantities by drawing them tail to head, force included. Okay. Now, in this question here, the one that they drew, okay, so you've got a car, and it's looks like it's maybe run out of, it says it's coasting, so it's run out of gas. Car's run out of gas, okay, but it's on a level road. So they got the force of gravity here, okay, they got the normal force here. Because the road is level, those two forces do what to each other? They cancel each other out. Okay, but they've drawn in 2 other forces directed backwards here. This one they call F air. Sometimes we call it drag. Okay, that would be the force of air resistance or friction traveling through the air. That would act backwards. Okay, and they also have this other one, force of friction. That would be the rolling friction between the tires and the road. Okay, there are 2 forces acting backwards. Since the car is coasting, there are no forces acting anywhere else, but namely forward. What's this car doing? Hey, slowing down. I mean, if you take your foot off the gas, your car slows down. Okay? You don't have to hit the brakes. Hitting the brakes makes it slow down faster because what does it do to this force if you hit the brakes? Makes it bigger. Okay? That's how brakes work. They increase the friction, right? The brake pads squeeze onto the rotor. Okay? Metal on metal, that's nice and frictiony. Okay? And so you'll slow down even faster. If the car is just coasting, there'd be rolling friction between the tires and the road. Okay? And there'd be air resistance over the car. Believe it or not, air resistance is kind of a big deal. Okay? Especially depending on the shape of your vehicle. Okay? If you drive a Jeep, you're pushing a brick through the air. Okay, your fuel economy is probably not all that good because your car is not very aerodynamic. Okay, whereas if you're driving a Tesla, it's like basically a teardrop. It's the most aerodynamic shape there is. Okay, that number would be low. All right, everybody okay with that idea? So if you had a Tesla and a Jeep side by side, and they both ran out of gas at the same time, the Tesla would definitely coast further. Okay, even though it's lighter, it would still coast further. Okay, because even though it has less inertia, there's also less forces acting on it because the drag would be so much less.
What about the Cybertruck?
Yeah, we won't talk about the Swaster truck. Yeah. Okay. All right, it's a dumpster. It looks like a dumpster. I don't get it. Okay, yeah, I think you just buy that to say I have one. I don't know. Does anyone know someone that has one? I don't get it. Okay, Does that make sense, the free body diagrams? Like I said, you don't have to go to the effort of this, okay? You do not have to draw a nice picture, just a box will do. Put the mass inside the box and you're good to go with your free body diagrams. Okay. Okay, in the situation we have there in that picture, okay, we got two people that are dragging a canoe out of a lake onto the beach using light ropes. Each person is exerting a force of 60 newtons forwards on the rope. Okay? The force of friction exerted by the beach on the canoe is 85 newtons backwards. Okay? So draw me a free body diagram of that situation. Okay? Give you a minute here. Just draw me a free body diagram of that situation. All right. So our free body diagram of this situation, okay, would be a box with 50 kilograms in the middle. All right. And there'd be, like, some people will do this. Some people will draw one force and say it's 120 newtons forward. And while numerically that's true, it's always good to show that this is actually two different forces going the same direction. Okay, just so that we know, right, that there's more than one force acting in that situation. Okay, so we would still put the two 60 Newton forces going forwards. Okay, off the front, and then 85 Newtons going to the back. All right, then they're collinear vectors, so we don't have to draw them tail to head if we don't want to. Okay, we can just go 120 minus 85 is going to be 35 newtons forwards. I think if my mental math would be right there. Okay, that would be the net force in that situation. Okay, so what is that canoe doing?
Floating.
Okay, what does the motion of it look like? Because there's a net force here now, right? If there's a net force, an unbalanced force acting on this object has to be, starts with A? Accelerating. Okay, net forces cause accelerations. Okay, so this canoe is accelerating up the beach. Okay? In the same way that we said when the car had a net force backwards, we said it was slowing down. Slowing down is still a change in velocity. It's a negative acceleration, but it's still an acceleration. Okay, everybody okay with that idea? All right. Now, here's the other thing we need to know, okay, about net force. Wait for time here. Okay, almost out of time. All right, so here's the other thing we need to know about net force. Net force is mass times acceleration. Right, and this is what we'll get into starting on Tuesday. Could I calculate right now, since I have the net force, 35 newtons forwards, and the mass of the canoe, 50 kilograms, could I calculate its acceleration? Okay, not a hard formula to manipulate it. Right, so it's like V equals D over T. It's a 3-variable formula. Okay, so all I would have to do is divide both sides by mass, and I'd have my acceleration. Okay, so I'd have 35 kilogram meters per second squared divided by 50 kilograms. What am I going to be left with for units? Meters per second squared. Okay. Okay, that's actually pretty reasonable. 0.7 meters per second squared up the beach, forwards, okay, whatever the appropriate vector would be on that one. All right, we'll start into that on Tuesday. For Monday, make sure you have a calculator with fresh batteries, a couple of pencils for sure. Okay, you'll have the usual bubble forms to fill in for the multiple choice and the numerical response, and then you'll show all of your work for the other written response questions. Okay? Make sure, guys, if you need to, you can look over any of the videos. They're all working again, so if you want to go into Google Classroom and see a few projectile motion or graphing, whatever, they go back. All the videos are live again and working. Okay? All right. We'll call it there, guys.